Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. In this presentation, we are going to explore GCP's Next Generation Firewall Enterprise with Intrusion Prevention Service. This is a powerful security capability that adds Layer 7 inspection to your Google Cloud workloads. Cloud NGFW represents Google's approach to distributed firewall services. Unlike traditional perimeter firewalls that sit at network boundaries, Cloud NGFW is fully distributed across your infrastructure. This means enforcement happens directly on each workload, enabling a true zero-trust security architecture. The key differentiator of Cloud NGFW Enterprise is its Intrusion Prevention Service, commonly referred to as IPS. This Layer 7 capability allows you to inspect traffic for malicious patterns, exploits, and threats in real time. What makes this particularly powerful is that you can add this advanced protection without redesigning your network architecture or changing routing configurations. Throughout this presentation, we will walk through setting up Cloud Next Generation Firewall Enterprise from scratch, including creating security profiles, configuring firewall endpoints, and testing intrusion prevention capabilities against actual attack simulations. Cloud Network Generation Firewall Benefits and Tiers. Let me explain the core benefits of Cloud Next Generation Firewall before we dive into the different tiers available. The first major benefit is that Cloud NGFW operates as a distributed firewall service. This means the firewall enforcement is stateful and fully distributed, running directly on each host. This architecture is fundamental to implementing zero-trust security because protection travels with the workload rather than relying on network boundaries. The second benefit relates to configuration and deployment simplicity. Cloud Next Generation Firewall implements network and hierarchical firewall policies that you can attach to different levels of your Google Cloud resource hierarchy. Whether you need policies at the organization level, folder level, or project level, you get a consistent firewall experience throughout. The third benefit is granular control and micro-segmentation. By combining firewall policies with IAM-governed tags, you achieve fine-grained control over both north-south traffic flowing in and out of your network and east-west traffic moving between resources. This control extends down to individual virtual machines across your VPC networks and even across your entire organization. Looking at the diagram, Cloud NGFW is available in 3 tiers. The Essentials tier provides basic firewall capabilities. The Standard tier adds features like threat intelligence and FQDN-based filtering. The Enterprise tier, which is our focus today, adds the Intrusion Prevention Service with Layer 7 inspection capabilities. Each tier builds upon the previous one, allowing you to choose the level of protection appropriate for your workloads. Cloud NGFW Enterprise Architecture. Now let me walk you through the architecture of Cloud Next Generation Firewall Enterprise and how the Intrusion Prevention Service integrates with your workloads. The diagram illustrates the complete flow of how traffic inspection works with Cloud Next Generation Firewall Enterprise. At the foundation, you have your VPC network, which is your isolated virtual network environment in GCP where all your resources reside. Within your VPC, you have workloads representing your compute instances, containers, or other resources that generate and receive network traffic. These workloads connect to the firewall endpoint, which is the actual inspection point where traffic gets analyzed. The firewall endpoint receives its inspection rules from the security profile group. This group acts as a container that references one or more security profiles, defining what threats to look for and how to respond. The security profile group connects to the security profile, which contains the actual threat prevention configuration. This is where you define the specific signatures, behaviors, and patterns that constitute threats in your environment. Finally, the security profile leverages the threat prevention profile, which is the underlying engine containing the detection rules and response actions. This profile uses Google's threat intelligence to identify and block known malicious patterns. The key insight here is that traffic flows from workloads through the firewall endpoint, where it gets inspected against the configured security profiles. If a threat is detected, the endpoint can block the traffic, alert you, or take other configured actions. All of this happens inline without requiring you to redirect traffic through separate appliances. Network Firewall Policies. Let me explain how Network Firewall Policies work and where they fit in Google Cloud's overall firewall architecture. A Network Firewall Policy acts as a container for firewall rules. You define rules within the policy, but these rules are not enforced until you associate the policy with a VPC VNet. Each VPC VNet can have one network firewall policy associated with it, giving you centralized control over that network security posture. One of the powerful features of network firewall policies is their support for IAM-governed tags. These tags replace the older network tags and provide identity to your workloads. Because these tags are managed through IAM, you get fine-grained access control over who can create, modify, and apply tags to resources. Looking at the diagram, Google Cloud's firewall policy hierarchy works in a specific order. Hierarchical firewall policies sit at the organization and folder levels, providing broad governance across multiple projects. Below that, you have VPC firewall rules, which are the traditional firewall rules applied directly to a VPC. Network Firewall Policies, available in both global and regional variants, provide more flexible policy management that can be shared across VPCs. The enforcement order matters significantly. By default, policies are evaluated in the order shown, but you can swap the order between VPC firewall rules and global network firewall policy using a G-Cloud command if your use case requires it. Every VPC also comes with implied firewall roles. There is a default egress allow role permitting all outbound traffic to any destination. Conversely, there is a default ingress deny role blocking all inbound traffic from any source. These implied roles provide a secure by default baseline that your explicit roles build upon. IAM-governed tags. Let me explain IAM-governed tags in detail because they are fundamental to how you will target firewall roles in Cloud NGFW. IAM-governed tags are key value pair resources that you define at either the organization level or project level in your Google Cloud resource hierarchy. Unlike simple labels, these tags are full cloud resources with their own IAM access controls. This means you can precisely specify which principals can create tag values, which can assign values to tags, and which can attach tags to resources. The diagram shows how tags work within the firewall policy context. You start by creating tag keys with a specific purpose designated for firewall use. Under each tag key, you create tag values representing the categories you want to use, such as client or server designations. These tag values then get bound to your instances through tag bindings. Once tags are bound to instances, your firewall rules can reference these tags in their target specifications. This creates a powerful abstraction where rules apply based on logical identity rather than IP's addresses or network location. An important characteristic of tags is that they follow Google Cloud's inheritance resource model. Tags and their values are passed down through the resource hierarchy from parent to child resources. This means you can create tags in one place and use them throughout your folders and projects. It is critical to distinguish IAM-governed tags from network tags. Network tags are simple strings attached to compute engine instances that disappear when the instance is deleted. They are not cloud resources and have no IAM access control. While VPC firewall rules can use network tags, the newer IAM-governed tags provide much stronger governance and are required for network firewall policies. Lab Environment Overview. Before we start building, let me walk you through the LAN environment we will create and the traffic flows we will inspect. Looking at the architecture diagram, we have the Internet represented as external traffic sources. traffic from the Internet first passes through the network load balancer, which distributes incoming requests to our backend servers. This load balancer has an external IP address that clients use to read our services. The load balancer connects to our web server, which is a compute instance running Apache that will serve as our target for testing attacks. This server sits in a public subnet within our VPC. We also have a client instance in the same subnet. This client serves two purposes. It generates internal east-west traffic to test intra-VPC inspection, and it generates outbound traffic that goes through Cloud NAT to reach external destinations. The Cloud NAT gateway provides outbound internet access for instances without public IP addresses. When we test north-south inbound traffic inspection, the client's traffic goes out through Cloud NAT and returns through the load balancer, simulating external attack traffic. The Cloud Next Generation Firewall endpoint sits between these components and the VPC network, inspecting traffic that matches our firewall roles. This endpoint is associated with our VPC and connected to our security profile group for threat detection. We will test two primary traffic flows. East-west inspection covers traffic between the client and server within the VPC. North-south inspection covers traffic entering from the Internet through the load balancer. Both flows will be inspected by Cloud NGFW Enterprise once we enable the inspection rules. Setting environment variables. Let me walk through the initial setup commands where we configure the environment variables that will be used throughout the lab. The first command is gcloudconfig set project followed by your project ID in square brackets, which you need to replace with your actual project identifier. This command sets your active project in Cloud Shell so all subsequent commands execute in the correct project context. Next, we define several environment variables using the export command. The project ID variable is set by querying gcloudconfig list with a format parameter that extracts just the project value from the core section. This dynamically retrieves your current project ID. The org ID variable uses gcloud projects get ancestors to find your organization ID. The command retrieves all ancestor resources of your project in CSV format without headers, filters for the raw containing organization as the type, and extracts just the ID portion before the comma. The region variable should be set to your preferred Google Cloud region, such as US Central 1 or Europe West 1. Similarly, the zone variable specifies your desired availability zone within that region. The prefix variable is set to Cloud NGFW and will be prepended to all resource names we create. This ensures consistent naming and makes cleanup easier. The org prefix uses the same value and is specifically for organization-level resources like Firewall Endpoints. Finally, billing project ID should be set to the project that will be billed for the Cloud Next Generation Firewall Enterprise endpoint. This is often the same as your project ID but can be different in organizations with centralized billing. Enabling required AP is. Before we can create Cloud Next Generation Firewall Enterprise resources, we need to enable several Google CP APIs. Let me explain each one. The first command enables the Compute Engine API with the identifier compute.googleapis.com. This API is required for creating virtual machines, networks, subnets, and other compute resources. Without this API enabled, you cannot provision any infrastructure. The second command enables the Network Security API identified as networksecurity.googleapis.com. This is the core API for Cloud Next Generation Firewall functionality, including creating firewall endpoints, security profiles, and security profile groups. All the advanced firewall features we will use depend on this API. The third command enables the Certificate Manager API with certificate-manager.googleapis.com. While we are not using TLS inspection in this lab, this API is part of the Cloud NGFW Enterprise prerequisite set and handles certificate management for encrypted traffic inspection scenarios. The fourth command enables the Network Services API using networkservices.googleapis.com. This API provides various network-related services that Cloud NGFW Enterprise depends on for its operation. The final command enables the Certificate Authority Service API with privatica.googleapis.com, similar to the Certificate Manager API. This supports TLS inspection scenarios where you need to create and manage certificate authorities. Even though we are not using TLS inspection today, enabling this API ensures all prerequisites are met. Running all these enable commands typically completes within a few seconds, and you only need to do this once per project. Creating security profile and group. Now we create the security profile and security profile group that define our threat prevention configuration. These are organization-level resources that can be shared across multiple projects. The first command creates a security profile of type threat prevention. The G-Cloud Network Security Profiles Threat Prevention Create command initiates the creation. The name is composed using the org_prefix variable followed by SP threat, creating a name like Cloud NGFW-SP-threat. The organization flag specifies this is an organization-level resource using our org_ID variable. The location is set to global because security profiles are global resources. After running this command, you will see a message indicating the system is waiting for the security profile to be created, followed by a done confirmation when complete. The second command creates a security profile group that references our security profile. The G-Cloud Network Security Profile Groups Create command starts the creation process. The group name uses org_prefix followed by SPG, resulting in something like Cloud NGFW-SPG. Again, we specify the organization and global location. The critical parameter here is Threat Prevention Profile, which creates the linkage between the group and our security profile. The value is the full resource path to our security profile, constructed as organization/org_ID/location/global/security profiles/the profile name. The security profile group is what you reference in your firewall roles when enabling inspection. It acts as an abstraction layer, allowing you to change the underlying profiles without modifying your firewall roles. Verifying and creating firewall endpoint. After creating the security profile and group, we verify they exist and then create the firewall endpoint, which is the actual inspection infrastructure. The first two commands verify our security resources were created successfully. The G-Cloud Network Security Profiles Threat Prevention List command with location set to global and organization set to org ID displays all threat prevention profiles in your organization. You should see the Cloud NGFW-SP-threat profile listed. Similarly, the G-Cloud Network Security Profile Groups list command shows all security profile groups. You should see Cloud NGFW-SPG in the output, confirming both resources exist. The third command creates the Cloud Next Generation Firewall Enterprise Endpoint, which is the compute infrastructure that actually inspects traffic. The G-Cloud Network Security Firewall Endpoints Create command takes the endpoint name composed of org prefix and zone variables. The zone parameter specifies where to deploy the endpoint. The organization flag indicates this is an organization resource. The billing project flag specifies which project pays for the endpoint. This endpoint creation takes approximately 20 minutes because G-Cloud is provisioning dedicated inspection infrastructure in your specified zone. While it provisions, the state shows as creating. The verification command G-Cloud Network Security Firewall Endpoints list shows your endpoints with their current state. Initially, you will see state creating. Once complete, this changes to state active, indicating the endpoint is ready to read traffic. You can get more details using the describe command, which shows the full resource path, creation timestamp, and current state. You should proceed with creating other lab resources while the endpoint provisions, checking back periodically until the state shows active. Creating VPC network and subnet. Now we begin creating the base infrastructure for our LAN environment. The first step is to create our VPC network and subnet where all our resources will reside. The first command creates a new VPC network using G-Cloud Compute Networks create. We pass the prefix variable followed by VPC to create a network named Cloud NGFW VPC. The subnet mode flag is set to custom, which means we will manually create subnets rather than having Google Cloud automatically create one subnet per region. Custom mode gives us precise control over our IP address space allocation. The second command creates a subnet within our newly created VPC. The G-Cloud Compute Networks subnets create command takes the subnet name composed of prefix, region, and subnet, resulting in something like Cloud NGFW-US-Central1-subnet. The range flag specifies the CIDR block 10.0.0.0/24, which provides 256 IPs addresses for our resources. This range falls within the RFC 1918 private address space and is commonly used for internal networks. The network flag references our VPC using the prefix variable, and the region flag places this subnet in our chosen region. Once created, this subnet becomes the home for our client instance, web server, and other compute resources. These two commands establish the foundational networking layer that all other resources will build upon. The VPC provides network isolation, while the subnet provides the actual IP address pool for our instances. Configuring Cloud NAT. With our VPC and subnet in place, we now configure Cloud NAT to provide outbound internet access for instances that do not have public IPs addresses. This is a best practice for security because it keeps your instances private while still allowing them to read the internet for updates and external API calls. The first command reserves a static external IP address using G-Cloud Compute Addresses create. We name it using prefix, region, and Cloud NAT IP, resulting in something like Cloud NGFW-US-Central1-Cloud NAT IP. The region flag ensures the IP address is allocated in our target region. Having a static IP for NAT is important because it provides a consistent source address that you can whitelist in external systems if needed. The second command exports the reserved IP address into a variable called Cloud NAT IP. We use G-Cloud Compute Addresses list with a filter to find addresses matching our naming pattern, then format the output to extract just the address value. This variable will be used later when creating firewall rules. The third command creates a cloud router, which is a prerequisite for Cloud NAT. The G-Cloud Compute routers create command names the router using prefix and CR. The region flag places it in our target region, and the network flag associates it with our VPC. Cloud router handles the BGP routing that Cloud NAT needs to function. The fourth command creates the Cloud NAT gateway itself using G-Cloud Compute routers NATs create. We name it using prefix, Cloud NAT, and region. The router flag associates it with our cloud router. The NAT all subnet IP ranges flag tells Cloud NAT to provide NAT services for all subnets in the VPC. The NAT external IP pool flag specifies our reserved static IP address as the NAT pool, meaning all outbound traffic will appear to come from this IP. Creating the web server instance. Now we create the web server instance that will serve as our target for attack simulation testing. This instance runs Apache Web Server and includes tools for traffic analysis. The G-Cloud Compute instances create command starts the instance creation. We name it using prefix, zone, and www, resulting in Cloud NGFW-US-Central1-a-www for example. The subnet flag places the instance in our previously created subnet. The no address flag is critical as it prevents assignment of a public IP, ensuring the instance only has a private IP and relies on Cloud NAT for outbound internet access. The zone flag specifies where to deploy the instance. The metadata startup script flag contains a bash script that runs when the instance first boots. Let me walk through this startup script in detail. The script begins with a pt-get update to refresh the package list. Then apt-get install Apache 2, TCP dump, IPF3, with the Y flag installs Apache Web Server, TCP dump for packet capture, and IPF3 for network testing without prompting for confirmation. The A2N site default secure sockets layer command enables the default secure sockets layer site configuration in Apache. The A2N mod secure sockets layer command enables the secure sockets layer module. These prepare Apache for HTTPS traffic. The script then reads virtual machine metadata to customize the web page. It sets MD_virtual machine to the metadata server URL. The virtual machine_host name variable uses curl to fetch the instance name from metadata, passing the metadata flavor header that Google CP requires. The filter variable contains an awk expression to extract the last field from path style values. The virtual machine_network and virtual machine_zone variables similarly fetch the network and zone information from metadata. Finally, the echo command creates a custom index.html page that displays the host name, network, and zone information. This customization helps identify which server responded during testing. The system control restart Apache 2 command ensures Apache loads the new configuration. Creating the client instance. After creating the web server, we create the client instance that will generate test traffic and simulate attacks against our web server. The G-Cloud Compute instances create command creates the client instance. We name it using prefix, zone, and client, resulting in something like Cloud NGFW-US-Central1-A-client. The subnet flag places it in the same subnet as our web server, which is necessary for testing east-west traffic inspection. The no address flag again ensures no public IP is assigned. The zone flag matches our web server's zone for optimal communication. The scopes flag is set to compute RO, which grants the instance read-only access to compute engine APIs. This scope allows the client to query information about other instances, which can be useful for discovering the web server's IP address dynamically. The metadata startup script flag contains a simpler script compared to the web server. The script runs apt-get update to refresh package lists. Then apt-get install with the Y flag installs Apache 2 utils for benchmarking tools like AB, IPF3 for network performance testing, and TCP dump for packet capture and analysis. Notice that this instance does not run a web server itself. It is purely a client for generating traffic. The Apache 2 utils package provides tools like AB and curl that we will use to send test requests and simulated attacks to the web server. The TCP dump utility allows us to capture packets to verify what traffic is being sent and read. Both instances are now deployed without public IPs, relying on Cloud NAT for outbound internet access and IAP for administrative SSH access. Creating project-level tags. Now we create IAM-governed tags at the project level that will be used to target our firewall rules. Tags provide identity to our workloads and enable fine-grained access control. Before creating tags, we may need to grant ourselves the appropriate IAM roles. The first two commands handle this. We export our user ID by querying G-Cloud auth list and extracting the account value. Then we use G-Cloud projects add IAM policy binding twice to grant ourselves the tag admin and tag user roles on the project. The tag admin role allows creating and managing tags, while the tag user role allows binding tags to resources. The third command creates the tag key using G-Cloud Resource Manager tags keys create. We name the key using prefix and VPC tags. The parent flag specifies this is a project-level tag using project/project ID format. The purpose flag is set to GCE Firewall, which indicates these tags will be used for firewall rules. The purpose data flag specifies which network can use these tags, formatted as network equal operator project ID/VPC name. The remaining commands create tag values under our tag key. Each G-Cloud Resource Manager tag's values create command creates a new value. The parent flag references our tag key using project ID/tag key name format. We create 3 values. Prefix VPC client for tagging client instances, prefix VPC server for tagging server instances, and prefix VPC quarantine for tagging instances that should be isolated. These tag values become available for binding to instances and for referencing in firewall roles. The quarantine tag is particularly useful for emergency isolation scenarios where you need to quickly cut off a compromised instance from all network traffic. Binding tags to instances. With our tags created, we now bind the appropriate tag values to our instances. This establishes the identity of each workload for firewall rule targeting. The first command binds the server tag to our web server instance. The G-Cloud Resource Manager tags bindings create command creates a binding between a tag value and a resource. The location flag specifies the zone where the target resource exists. The tag value flag references the full path to our server tag value using project ID, tag key name, and tag value name. The parent flag specifies the target resource using the full compute engine resource path format :/compute.googleapis.com/projects/project ID/zones/zone/instances/instance name. The second command follows the same pattern but binds the client tag to our client instance. We use the same location and similar parent format, just changing the tag value to reference the client tag and changing the instance name to our client instance. Once these bindings are in place, our firewall rules can use target secure tags to apply rules only to instances with specific tags. For example, a rule targeting the server tag will only affect our web server, while a rule targeting the client tag will only affect our client instance. This tag-based approach is much more flexible than IP-based roles because tags travel with the instance identity regardless of IP address changes. If you recreate an instance with the same tag binding, the firewall roles automatically apply without modification. Looking at the diagram, the tag binding flow connects tag values to specific compute instances through bindings, and those tags then allow firewall rules to target specific workloads based on their assigned identity. Creating Global Network Firewall Policy. Now we create the Global Network Firewall Policy that will contain all our firewall roles. This policy provides a centralized container for managing security roles across our VPCs. The G-Cloud Compute Network Firewall Policies create command creates a new firewall policy. We name it using prefix and FW policy, resulting in Cloud NGFW FW policy. The description flag provides a human-readable explanation, which we set to Cloud NGFW Enterprise to indicate the policy's purpose. The global flag indicates this is a global policy rather than a regional one, meaning it can be associated with VPCs in any region. At this point, the policy exists but contains no rules and is not associated with any VPC. Rules will be added in subsequent steps, and the policy must be explicitly associated with our VPC before any rules take effect. Looking at the diagram, the policy structure shows how a global network firewall policy contains multiple rules at different priorities. Rules are evaluated in priority order, with lower numbers evaluated first. Each rule specifies an action, direction, target, source or destination, and layer 4 configuration. The policy then gets associated with one or more VPCs where its rules become enforced. This architecture allows you to create a single policy with comprehensive rules and then share it across multiple VPCs, ensuring consistent security posture throughout your organization. Any changes to the policy automatically propagate to all associated VPCs. Creating Cloud Firewall Essential Rules. With our policy container created, we now add Cloud Firewall Essential Tier rules. These rules provide basic allow and deny functionality based on tags and IP ranges. The first rule at priority 100 blocks all traffic from quarantined workloads. The G-Cloud Compute Network Firewall Policies rules create command adds a rule to our policy. Priority 100 means this rule is evaluated early. The description explains the rule blocks quarantined workloads. The action is deny, which drops matching traffic. The firewall policy flag references our policy, and global firewall policy indicates it is a global policy. The layer 4 configs is set to all, matching any protocol. The direction is egress for outbound traffic. The target secured tags flag references our quarantine tag, so only instances with this tag are affected. The dest IP ranges of quad 0/0 means all destinations. This rule effectively isolates any quarantined instance from all network communication. The second ROT at priority 1000 allows health check traffic to servers. The action is allow. The layer 4 configs specifies TCP/80 and TCP/443 for HTTP and HTTP pages S. The direction is ingress for inbound traffic. The target secured tags references the server tag. The source IP ranges includes Google's HealthCheck IP ranges 35.191.0.0/16, 130.211.0.0/22, 209.85.152.0/22, and 209.85.204.0/22. This allows load balancer health checks to read our web server. The third ROT at priority 2000 allows SSH from identity-aware proxy. The action is allow. The layer 4 configs specifies TCP:22 for SSH. The direction is ingress. The source IP ranges is 35.235.240.0/20, which is Google's IAP range. This enables secure SSH access through IAP tunneling without requiring public IPs on instances. Creating Cloud Firewall Standard Rules. Now we add Cloud Firewall Standard Tier rules that leverage threat intelligence and FQDN-based filtering. These rules provide enhanced protection against known malicious sources and destinations. The first ROT at priority 3000 blocks ingress from dangerous sources. The action is deny. The layer 4 configs is all for any protocol. The direction is ingress. The source region codes flag specifies embargoed countries. CU for Cuba, IR for Iran, KP for North Korea, SY for Syria, XC for Crimea, and XD for disputed regions. The source threat intelligence flag adds two threat intelligence lists. IP list Tor exit nodes to block traffic from Tor exit nodes, and IP list known malicious IPs to block known malicious IP addresses. This ROT stops traffic from high-risk sources before it reaches your workloads. The second ROT at priority 4000 mirrors the previous ROT but for egress traffic. The direction is egress, and we use dest region codes and dest threat intelligence instead of source variants. This prevents your workloads from communicating with dangerous destinations, even if compromised. The third ROT at priority 5000 allows outbound traffic to specific fully qualified domain names for system updates. The description indicates this allows system updates. The action is allow. The layer 4 configs specifies TCP/80 and TCP/443. The direction is egress. The dest fully qualified domain names flag specifies fully qualified domain names that should be allowed. ftp.us.debian.org for Debian packages, debian.map.fastly.net for Debian CDN, packages.cloud.googleoffice.com for Google Cloud Packages, and www.l.googleoffice.com for Google Services. This allows your instances to receive security updates while blocking other outbound traffic. These standard tier features significantly enhance your security posture by leveraging Google's threat intelligence and allowing precise control over which external domains your workloads can access. Creating ingress allow rules and policy association. Now we create the final ingress routes that allow traffic from specific sources to our servers. These rules will later be modified to enable Cloud Next Generation Firewall Enterprise Inspection. The first route at priority 6000 allows internal traffic from the subnet. The description explains it allows ingress internal traffic from clients. The action is allow for now, but this will change to apply security profile group when we enable inspection. The firewall policy and global firewall policy flags reference our policy. The direction is ingress. The enable logging flag turns on firewall logging so we can read which traffic matches this route. The layer 4 configs is all to match any protocol. The source IP ranges is 10.0.0.0/24, which is our subnet CIDR. The target secure tags references the server tag. This route allows east-west traffic within our VPC to read tagged servers. The second route at priority 7000 allows external traffic through the load balancer. The description indicates it allows ingress external traffic to server. The action is allow initially. The layer 4 configs specifies TCP:80 and TCP:443. The direction is ingress with enable logging. The source IP ranges references our Cloud NAT IP variable, which is the Cloud NAT external IP. This may seem unusual, but remember our test traffic goes out through NAT and returns through the load balancer, so the source appears as the NAT IP. The target secure tags references the server tag. The final command associates our firewall policy with the VPC. The G-Cloud Compute Network Firewall Policies associations create command links the policy to a network. The firewall policy flag specifies our policy. The network flag specifies our VPC. The name flag creates a named association for easy reference. The global firewall policy flag indicates the policy type. Once associated, all rules in the policy become active for the VPC, and traffic is evaluated against them in priority order. Creating external network load balancer, Part 1. Now we create the external TCP/UDP network load balancer that will provide public access to our web server. This load balancer enables north-south traffic inspection testing by allowing external traffic to reach our internal server. The first command reserves an external IP address for the load balancer using G-Cloud Compute addresses create. We name it using prefix, region, and NLBIP, resulting in something like Cloud NGFW-US Central 1-NLBIP. The region flag ensures the IP is allocated in our target region. This static IP becomes the public entry point for accessing our web server. The second command creates an unmanaged instance group. The G-Cloud Compute Instance Group's unmanaged create command creates a container for grouping instances. We name it using prefix and IG. The zone flag specifies where the group exists. Unmanaged instance groups are simpler than managed instance groups because you manually add and remove instances rather than using templates and autoscaling. The third command adds our web server to the instance group. The G-Cloud Compute Instance Group's unmanaged add instances command takes the group name. The instances flag specifies which instance to add using our web server name. The zone flag indicates where both the group and instance reside. After this command, our web server becomes a backend target for the load balancer. The fourth command creates a regional health check. The G-Cloud Compute Health Checks create HTTP command creates an HTTP health check. We name it using prefix, region, and HC-HTTP80. The region flag makes this a regional health check. The port flag specifies port 80 for HTTP health probes. The load balancer uses this health check to determine if our web server is healthy and able to read traffic. Creating external network load balancer Part 2. With the IP address, instance group, and health check created. We now configure the backend service and forwarding role to complete the load balancer setup. The first command creates the backend service using G-Cloud Compute Backend Services create. We name it using prefix and NLB-BES. The protocol flag is set to TCP because this is a TCP/UDP network load balancer, not an HTTP/HTTPS load balancer. The health checks flag references our previously created health check. The health checks region flag specifies the region of the health check. The region flag indicates this is a regional backend service. The second command adds our instance group as a backend to the service. The G-Cloud Compute Backend Services add backend command takes the backend service name. The instance group flag specifies our instance group. The instance group zone flag indicates where the instance group resides. The region flag specifies the backend services region. After this, traffic sent to the backend service will be distributed to instances in our instance group. The third command creates the forwarding route that ties everything together. The G-Cloud Compute Forwarding Routes Create command creates a route named using prefix and NLB-IPv4. The load balancing scheme flag is set to external, meaning this is an external-facing load balancer accessible from the internet. The region flag places it in our target region. The ports flag specifies port 80 for HTTP traffic. The address flag references our reserved external IP. The backend service flag connects the forwarding route to our backend service. Once complete, traffic hitting our external IP on port 80 flows through the forwarding role to the backend service, which distributes it to healthy instances in our instance group. Verifying firewall endpoint status. Before we can associate the firewall endpoint with our VPC, we must verify that the endpoint creation completed successfully. Remember that endpoint provisioning takes approximately 20 minutes. The first command checks the endpoint status using G-Cloud Network Security Firewall Endpoints list. The zone flag filters to show only endpoints in our target zone. The organization flag specifies the organization that owns the endpoint. The output shows the endpoint ID, location, and most importantly, the state field. When the endpoint is still being created, you will see state creating in the output. You must wait until this changes to state active before proceeding. If you try to associate a creating endpoint with a VPC, the association will fail. The second command provides more detailed information using G-Cloud Network Security Firewall Endpoints describe. We pass the endpoint name composed of org prefix and zone. The organization flag specifies the owning organization. The zone flag indicates the endpoint location. The describe output includes the create time showing when provisioning started, the full resource name path, the current state, and the update time showing the last status change. When state shows active, the endpoint is ready for association. If you have been following along and created other resources in parallel, approximately 20 minutes should have passed. If the endpoint is not yet active, you will need to wait and check again periodically. The endpoint must be fully provisioned before it can inspect any traffic. Associating endpoint with VPC. With the firewall endpoint in active state, we now create an association between the endpoint and our VPC network. This association enables the endpoint to inspect traffic within the VPC. The G-Cloud Network Security Firewall Endpoint Associations Create command creates the association. We name it using prefix and association, resulting in Cloud NGFW association. The zone flag specifies where the endpoint resides. The network flag references our VPC using prefix VPC. The endpoint flag specifies which endpoint to associate using org_prefix and zone. The organization flag indicates the organization owning the endpoint. The association process itself takes approximately 10 minutes. During this time, Google CDN configures the necessary routing and integration between your VPC and the firewall endpoint infrastructure. After running the create command, Use G-Cloud Network Security Firewall Endpoint Associations list to check the status. Initially, you will see state creating. Only proceed once the state changes to state active. The list output shows the association ID, location, network name, endpoint name, and state. When the state shows active, the endpoint is ready to inspect traffic that matches your firewall rules. You can also use the describe command for more details. The output includes create time, the full firewall endpoint resource path, the association name, the network path, state, and update time. This information is useful for troubleshooting if the association fails or takes longer than expected. Once the association is active, any firewall rules with the Apply Security Profile Group action will route matching traffic through the endpoint for Layer 7 inspection. Connecting to client instance via SSH. With all infrastructure as a service in place, we now connect to the client instance to begin testing. Since our instances have no public IP addresses, we use identity-aware proxy to tunnel our SSH connection securely. The G-Cloud Compute Secure Shell command initiates the Secure Shell connection. We specify the instance name using prefix, zone, and client. The tunnel through IAP flag tells G-Cloud to route the Secure Shell connection through identity-aware proxy rather than attempting a direct connection. The zone flag specifies where the instance is located. When you run this command, G-Cloud establishes an IAP tunnel from your local machine to the instance. IAP verifies your identity using your Google Cloud credentials and checks that you have the necessary IAM permissions to access the instance. This approach is more secure than exposing Secure Shell directly to the Internet because access is controlled through IAM rather than firewall routes and Secure Shell keys alone. Once connected, you will have a shell prompt on the client instance. The first thing we need to do in this new session is redefine our environment variables because the SSH session starts with a fresh environment. We export the region variable with our target region value. We export the zone variable with our target zone. We export the prefix variable set to Cloud NGFW. Then we use G-Cloud commands to dynamically read the web server's private IP and the load balancer's external IP, storing them in target private IP and target NLB IP variables respectively. The target private IP command uses G-Cloud Compute Instances list with a filter for our web server name, then formats the output to extract just the network interface's .network IP value. The target NLB IP command similarly lists addresses filtered by our NLB IP name and extracts the address value. Testing baseline connectivity. Before we enable inspection, we need to verify that our basic connectivity works. We test both the internal east-west path and the external north-south path. The first curl command tests connectivity to the web server's private IP address. We run curl with target private IP and a max time of 2 seconds to prevent hanging. This tests east-west traffic within the VPC. If successful, you should see the response showing the page content with host name, network, and zone information. The second curl command tests connectivity through the load balancer. We curl the target _NLB IP address, which is our load balancer's external IP. The max time flag again prevents hanging. This traffic flow is more complex. Our request goes out through Cloud NAT to the Internet, then returns through the load balancer to our web server. This simulates how external clients would access the server. Both curl commands should return the same response since they ultimately reach the same web server. The expected output shows the custom page we configured in the startup script. Page on Cloud NGFW Zone www in Network Cloud NGFW VPC Zone, with your actual zone values inserted. If either curl command fails or times out, you need to troubleshoot before proceeding. Common issues include firewall roles not being properly associated, the health check failing so the load balancer marks the backend unhealthy, or network configuration problems. Verify each component is in the expected state before moving forward. This baseline test confirms that without Layer 7 inspection enabled, traffic flows normally through your network. We will repeat similar tests after enabling inspection to observe the difference when attacks are detected. Sending sample attacks east-west traffic. Now we send sample attack traffic to test our baseline security posture before enabling Cloud Next Generation Firewall Enterprise inspection. These attacks target the internal server IP, testing east-west inspection. The first attack is a shellshock exploit attempt. The curl command uses the H flag to set a custom user agent header. The header value contains the shellshock payload, parentheses, space, parentheses, space, colon, semicolon, semicolon, followed by a fake IP and port. This exploits a vulnerability in Bash where environment variables containing function definitions could execute arbitrary commands. We target the CGI bin/test critical path on our private IP. The M flag sets a 3-second timeout. The second attack attempts directory traversal. The curl command targets a path containing multiple .. sequences to escape the webroot directory and access system files. The path tries to read /etc/password through the CGI bin handler. This attack exploits improper input validation that allows accessing files outside the intended directory. The third attack is another directory traversal variant targeting Windows systems. The path includes ////wint/win.ini, which would access the Windows initialization file on a vulnerable Windows server. While our Apache server runs on Linux, this tests whether the IPS detects Windows-targeted attacks. The fourth attack simulates a command injection attempt. The URL includes a username parameter with a malicious payload that attempts to download and execute a remote script. The payload tries to change directory to /tmp, download a file called evil using wget, execute it with sh, and delete it to cover tracks. Without inspection enabled, all these attacks reach the web server. Apache returns 404 not found or 400 bad request responses because the exploited paths do not exist, but the malicious traffic was not blocked at the network layer. Sending sample attacks. North-south traffic. After testing east-west attacks, we repeat the same attacks against the external load balancer IP to test north-south traffic inspection. This simulates attacks from the internet. The first attack sends the shellshock payload to the load balancer IP. The curl command structure is identical to the east-west test, but target_NLB IP replaces target_private IP. The traffic flows out through CloudNet, across the internet, and back in through the load balancer. This path simulates how an external attacker would attempt to exploit your public-facing services. The second attack repeats the directory traversal to /etc/password against the external IP. Again, the command is the same except for the target IP address. The third attack sends the Windows directory traversal attempt to the external endpoint. Even though we know the server runs Linux, security products should detect and potentially block attacks targeting any platform. The fourth attack sends the command injection payload through the load balancer. This wget-based remote code execution attempt represents a common attack pattern where adversaries try to download and execute malware. The expected responses match the east-west tests. 404 not found for paths that do not exist, and 400 bad request for malformed requests. The web server responds to all requests because no Layer 7 inspection is blocking them. These baseline tests demonstrate that without Cloud Next Generation Firewall Enterprise inspection enabled, malicious traffic patterns pass through your firewall rules as long as they match the allow criteria. The rules only examine Layer 3 and Layer 4 characteristics like IP addresses, ports, and protocols. The actual payload content is not inspected. Understanding the attack response patterns. Let me explain the responses we read from our attack tests, so you understand what to expect before and after enabling inspection. The first two attack patterns, shellshock and directory traversal to /etc/password. Return 404 not found responses. This HTML response from Apache indicates the requested path does not exist on the server. The CGI bin/test critical and the traversal paths are not valid resources. The server did not execute any malicious code, but importantly, the malicious request did reach the server and was processed. The third attack pattern, the Windows directory traversal, returns the normal page content. This happens because the query parameter format does not cause Apache to interpret it as a path traversal. Apache treats it as a regular request to the root page with a query string. The attack signature is still present in the traffic, but Apache ignores it. The fourth attack pattern, the command injection, returns a 400 bad request response. Apache cannot parse the malformed URL containing shell commands and special characters. The server rejects the read request at the HTTP parsing layer. The key insight is that these responses come from Apache, not from any security system. Apache happens to reject or not execute these particular payloads due to how it processes requests, but this is not reliable protection. More sophisticated attacks or attacks targeting actual vulnerabilities would succeed. When we enable Cloud Next Generation Firewall Enterprise Inspection, the firewall endpoint examines the packet content before it reaches Apache. If a threat signature matches, the endpoint can reset the connection, preventing the malicious traffic from ever reaching the server. You will see connection reset or timeout errors instead of Apache responses. Summary ready to enable inspection. Let me summarize what we have built so far and what comes next as we prepare to enable Cloud Next Generation Firewall Enterprise Inspection. We have created a complete LAN environment with a VPC network and subnet, Cloud NAT for outbound internet access, a web server running Apache, a client instance for generating traffic, and an external network load balancer for public access. We configured IAM-governed tags to identify our workloads and created a comprehensive firewall policy with essential tier rules for basic allow/deny and standard tier rules for threat intelligence and geo-blocking. We also created the Cloud Next Generation Firewall Enterprise components, a security profile defining our threat prevention configuration, a security profile group referencing the profile, and a firewall endpoint deployed in our zone. We associated the endpoint with our VPC, enabling it to inspect traffic. Our baseline tests confirmed that both east-west traffic between client and server and north-south traffic through the load balancer worked correctly. We then sent sample attacks representing common exploit patterns, shellshock, directory traversal, and command injection. All attacks reached the web server because our current firewall rules use the allow action, which only examines layer 3/4 characteristics. In the next section, we will update the firewall rules to use the apply security profile group action instead of allow. This change routes matching traffic through the firewall endpoint for layer 7 inspection. After the update, we will repeat our attack tests and observe how Cloud NGFW Enterprise detects and blocks the malicious traffic patterns. The key difference will be the responses. Instead of Apache returning 404 or 400 errors, you will see connection resets and timeouts as the firewall endpoint terminates malicious connections before they read the server. Enabling Layer 7 inspection updating Rule 6000. Now we move to the critical step of enabling Cloud NGFW Enterprise inspection. We will update our existing firewall rules to route matching traffic through the firewall endpoint for Layer 7 analysis. Switch back to Cloud Shell from your secure shell session on the client virtual machine. We need to run these update commands from Cloud Shell because they modify organization-level resources that require appropriate permissions. The G-Cloud Compute Network Firewall Policies Rules Update command modifies an existing rule. We specify Rule Priority 6000, which is our rule for internal east-west traffic. The action flag changes from allow to apply security profile group. This is the key change that enables inspection. The firewall policy flag references our policy name, The enable logging flag ensures we capture logs for traffic matching this rule. The global firewall policy flag indicates this is a global policy. The security profile group flag specifies which profile group to use for inspection. The value is the full resource path starting with /networksecurity.googleapis.com, followed by organizations, your org ID, locations, global, security profile groups, and finally your profile group name. This path tells the firewall which threat prevention configuration to apply. After running this command, any traffic matching ROT 6000 will be routed through the firewall endpoint. The endpoint inspects the traffic against the threat signatures defined in your security profile. If a threat is detected, the endpoint takes the configured action, typically blocking the connection. Enabling Layer 7 inspection updating Rule 7000. After updating ROL 6000 for east-west traffic, we apply the same change to ROL 7000 for north-south traffic through the load balancer. The command structure is identical to the previous update. We use G-Cloud Compute Network Firewall Policies Rules Update with priority 7000. The action changes to apply security profile group. We include firewall policy, enable logging, and global firewall policy flags. The security profile group flag uses the same profile group path. This ensures consistent threat detection configuration across both traffic paths. Whether traffic comes from within the VPC or from external sources through the load balancer, it receives the same level of inspection. With both rules updated, our firewall policy now performs Layer 7 inspection on all traffic destined for tagged servers. The firewall endpoint examines packet payloads, not just headers, looking for patterns that match known attack signatures. The transition from allow to apply security profile group is transparent to legitimate traffic. Normal requests pass through the endpoint with minimal latency impact. Only traffic matching threat signatures triggers blocking or alerting actions. Let me also explain what happens during inspection. When traffic matches a ROT with apply security profile group, the firewall endpoint receives a copy of the packet. The endpoint's inspection engine analyzes the payload against thousands of threat signatures. If no threat is found, the traffic proceeds normally. If a threat is detected, the endpoint can reset the connection, drop packets, or take other configured actions while logging the event. Verifying updated firewall rules. After updating the rules, we verify that the changes were applied correctly. This verification step ensures our inspection configuration is active before we test. The first command describes Rule 6000 using G-Cloud Compute Network Firewall Policies rules describe. We pass the priority 6000, the firewall policy name, and the global firewall policy flag. The output shows all rule attributes. In the output, look for several key fields. The action field should now show apply security profile group instead of allow. The description confirms this is the internal traffic ROT. The direction shows ingress. The enable logging field shows true. The match section displays the layer 4 configs and source IP ranges. Most importantly, the security profile group field shows the full path to your profile group, confirming the inspection configuration is attached. The Target Secured Tags section shows which tags this rule applies to, and the state shows effective, meaning the rule is actively being enforced. We run the same describe command for Rule 7000 to verify the external traffic ROT. The output structure is similar, with the key difference being the source IP ranges showing your Cloud NAT IP instead of the internal subnet range, and the Layer 4 configs showing specific TCP ports 80 and 443 rather than all protocols. If either ROL shows action allow instead of action apply security profile group, the update did not succeed. Rerun the update command and check for any error messages. Common issues include incorrect security profile group paths or permission problems. Testing attacks with inspection east-west. With inspection enabled, switch back to your secure shell session on the client virtual machine and rerun the attack tests. We will see dramatically different results now that the firewall endpoint is analyzing traffic. Run the same 4 attack commands against the internal server IP. The first attack sends the shellshock payload using the malicious user agent header to the private IP. The second attack attempts directory traversal to access /etc/password. The third attack tries the Windows directory traversal through a query parameter. The fourth attack sends the command injection payload with wget. This time, the responses are completely different. For the shellshock attack, instead of a 404 response from Apache, you see curl : left parenthesis 56 right parenthesis recv failure : connection reset by peer. This error means the connection was forcibly terminated. The firewall endpoint detected the shellshock signature in the user agent header and reset the TCP connection before the request could read Apache. For the directory traversal attacks, you see curl 28 operation timed out after 3000 milliseconds with 0 bytes received. The firewall endpoint detected the traversal pattern and silently dropped the packets. Without receiving a response or a reset, curl waits until the timeout expires. The fourth attack, command injection, may still return a 400 bad request. This particular payload structure causes Apache to reject it before the full malicious content is processed. However, Cloud NGFW still logged the threat even though Apache's response reached the client. The key observation is that high-severity attacks are now being blocked at the network layer, never reaching the application. This is true intrusion prevention, not just detection. Testing attacks with inspection north-south. After testing east-west inspection, we repeat the attacks through the external load balancer IP to verify north-south inspection is working. Run the same 4 attack commands, but this time target the target_NL-BIP variable instead of the private IP. The shellshock attack goes to the load balancer IP with the malicious header. The directory traversal attacks target the external endpoint. The command injection payload is sent through the public path. The results match the east-west tests. The shellshock attack returns connection reset by peer. The directory traversal attacks timeout waiting for a response. The web application firewall endpoint intercepts these attacks regardless of whether they arrive through internal paths or external load balancer paths. This consistency demonstrates that Cloud Next Generation Firewall Enterprise provides unified protection. Your security profile group defines the threat signatures and actions, and those definitions apply everywhere the profile is referenced. Whether an attacker is inside your network performing lateral movement or outside attempting to breach your perimeter, the same detection and prevention capabilities protect your workloads. The expected output section shows the pattern you should see. Connection reset for some attacks, timeout for others, and occasionally a 400 response for malformed requests that Apache catches before full processing. All of these represent successful threat mitigation because the malicious payload did not execute on the target system. If you still see 404 not found responses from Apache, the inspection is not working correctly. Verify that both roles show apply security profile group action, the endpoint association is active, and the security profile group path is correct. Viewing threat logs in Cloud Console. Cloud Next Generation Firewall Enterprise logs all detected threats to cloud logging. We can read these logs in the Cloud Console to see details about each blocked attack. Navigate to Network Security in the Cloud Console, then select Threats from the left menu. This view shows a summary of detected threats across your environment. You may need to refresh the page a few times before the attacks appear. There is typically a short delay between when the firewall endpoint detects a threat and when the log entry appears in the console. This delay is usually just a few seconds but can occasionally take a minute or two. The Threats view displays a table with columns for timestamp, severity, threat name, source IP, destination IP, and other relevant details. You should see entries corresponding to the attacks we sent. The severity column indicates how critical each threat is, with values like high or critical, for the exploits we tested. Click on any threat entry to read more details. The expanded view shows the full threat signature name, the exact packet data that triggered the detection, source and destination ports, protocol information, and the action taken by the firewall endpoint. Each threat entry also has a view audit log link. Clicking this opens the threat in Cloud Logging's Log Explorer, where you can see the complete JSON log entry with all fields. This is useful for building automated alerting or integrating with SIEM systems. The audit log view provides even more granular information, including the specific firewall route that matched, the security profile group used, and timing information for the inspection process. Analyzing threat log details. Let me walk through the specific fields you will see in the threat logs and what each one means for your security analysis. The threat log entries appear under the resource type networksecurity.googleapis.com/firewall endpoint. You can use this as a filter in Log Explorer to show only Cloud NGFW enterprise threat events. Each log entry contains a JSON payload with detailed information. The threat name field identifies the specific vulnerability or attack pattern detected, such as Apache Strut's remote code execution or directory traversal attempt. The threat ID is a unique identifier for the signature that matched. The severity field indicates the threat level: critical, high, medium, low, or informational. Our test attacks should appear as high, or critical, severity because they represent active exploitation attempts. The source IP and destination IP fields show where the traffic originated and where it was headed. For east-west attacks, you will see internal IP addresses. For north-south attacks through the load balancer, the source appears as your CloudNet IP because that is where the traffic entered the inspection path. The action field shows what the firewall endpoint did: block, alarm, or allow depending on your profile configuration. For our default threat prevention profile, high-severity threats are blocked. The rule details section shows which firewall rule triggered the inspection. The action field here shows apply security profile group, confirming the traffic was sent for Layer 7 analysis. This helps correlate threat events with specific firewall policy rules. Understanding these log fields enables you to build effective monitoring dashboards, create alerting policies for specific threat types, and integrate Cloud Next Generation Firewall Enterprise with your broader security operations workflows. Verifying intercepted packets with log filter. Beyond threat logs, you can also verify that Cloud NGFW is intercepting packets by filtering for the firewall rule action in Log Explorer. This is useful for troubleshooting and confirming inspection is active. In Cloud Logging's Log Explorer, enter the filter JSON payload.rule-details.action=operator, apply_security_profile_group. This query shows all log entries where traffic was routed through the firewall endpoint for inspection. The results include both traffic that triggered threat alarms and clean traffic that passed inspection without issues. This broader view helps you understand the volume of traffic being inspected and verify that your rules are matching the expected flows. Each log entry shows the connection details including source IP, destination IP, ports, protocol, and the route priority that matched. The disposition field indicates whether the connection was allowed or blocked after inspection. You can further refine your queries to focus on specific scenarios. Adding source IP filters shows traffic from particular hosts. Adding destination port filters shows traffic to specific services. Combining filters helps isolate exactly the traffic flows you want to analyze. This logging capability is valuable for security operations. You can create log-based metrics to track inspection volume over time, build alerting policies for unusual patterns, and export logs to external SIEM platforms for correlation with other security data. The combination of threat-specific logs and general inspection logs gives you complete visibility into how Cloud NGFW Enterprise is protecting your workloads. Optional Internet Traffic Inspection. The inspection we configured so far covers intra-VPC east-west traffic and inbound north-south traffic. Optionally, You can also inspect outbound internet traffic by creating an egress route. Back in Cloud Shell, create a new route at priority 10,000. The G-Cloud Compute Network Firewall Policies roles create command adds the role. The description indicates this inspects all egress internet traffic from clients. The action is apply security profile group to enable inspection. The firewall policy and global firewall policy flags reference our policy. The Layer 4 configs specifies TCP:80 and TCP:443 for HTTP and HTTPS traffic. The direction is egress for outbound traffic. The destination IP ranges as quad 0/0, meaning all internet destinations. The enable logging flag captures logs for this route. The target secure tags flag references the client tag, so only client-tagged instances have their egress inspected. The security profile group flag points to our profile group. After creating this route, switch back to the client virtual machine and resend the attacks to the external load balancer IP. The traffic now gets inspected on the egress path before leaving the client, rather than on the ingress path at the server. In the threat logs, you will see the attacks detected again, but this time the source IP shows the internal client IP instead of the CloudNet IP. This is because the egress role inspects traffic before it goes through NAT, capturing the true source. Egress inspection is valuable for detecting compromised workloads attempting to communicate with command and control servers or exfiltrating data. By inspecting outbound traffic, you catch threats that originate from inside your network. Inspection flow summary. Let me summarize the complete traffic inspection architecture we have built and how the different components work together. Looking at the architecture diagram, we have 3 inspection scenarios. For east-west traffic, the client sends a request to the server's private IP. The request matches firewall route 6000 because it comes from the subnet 10.0.0.0/24 and targets a server-tagged instance. The rules apply security profile group action routes the traffic to the firewall endpoint. The endpoint inspects the payload, detects any threats, and either allows or blocks the connection. For north-south inbound traffic, the client's request goes out through CloudNet to the internet, then returns through the load balancer to the server. Route 7000 matches because the source IP is the CloudNet address and the destination is a server-tagged instance. The traffic goes through the same inspection process at the firewall endpoint. For outbound internet traffic with the optional egress rule, client traffic destined for any internet address matches Rule 10,000. The inspection happens before the traffic leaves through CloudNet, capturing the internal source IP in logs. The firewall endpoint is the central inspection point for all these flows. It connects to the security profile group, which references the security profile containing threat detection rules. When a threat matches, the endpoint blocks the connection and creates a log entry. When traffic is clean, it passes through with minimal latency. This architecture provides comprehensive protection across all traffic directions without requiring changes to your application code, network topology, or routing configuration. You simply update firewall roles to enable inspection, and Cloud NGFW Enterprise handles the rest. Enterprise capabilities. It is important to clean up all the resources we created. This prevents ongoing charges and keeps your environment tidy. The cleanup process must follow a specific order because of resource dependencies. You cannot delete a firewall endpoint while it still has VPC associations. You cannot delete a security profile while it is referenced by a security profile group. Following the correct sequence ensures smooth deletion without errors. Looking at the cleanup sequence diagram, we start by deleting the Cloud Next Generation Firewall Enterprise components first. The endpoint association must be removed before the endpoint itself. After the endpoint is deleted, we remove the security profile group and then the security profile. Once the Cloud Next Generation Firewall Enterprise resources are gone, we proceed to the base infrastructure. The load balancer components come first, followed by compute instances, then tags and tag bindings, the firewall policy and its association, CloudNAT and Cloud Router, reserved IP addresses, and finally the subnet and VPC network. Each step includes verification commands to confirm deletion before proceeding. This methodical approach prevents orphaned resources and ensures complete cleanup. Some deletions, particularly the firewall endpoint, take significant time, so plan accordingly. Let me walk you through each cleanup step in detail over the next several slides. Deleting endpoint association. The first cleanup step is removing the firewall endpoint association from your VPC. This disconnects the endpoint from your network and stops traffic inspection. Before deleting, list existing associations to confirm what needs to be removed. The G-Cloud Network Security Firewall Endpoint Associations List command shows all associations in your project. Verify you read the Cloud NGFW association we created earlier. The delete command uses G-Cloud Network Security Firewall Endpoint Associations delete followed by the association name, which is constructed from prefix and association. The zone flag specifies where the association exists. When you run this command, you will be prompted to confirm the deletion. Type Y and press Enter to proceed. The deletion typically completes within a few minutes as Google Cloud removes the routing configuration that directed traffic to the endpoint. After the delete command finishes, run the list command again to verify the association no longer appears. If you see an empty result or the association is missing from the list, the deletion was successful. With the association removed, the firewall endpoint still exists but is no longer connected to any VPC. Traffic in your VPC now flows without Layer 7 inspection, reverting to the behavior before we enabled Cloud Next Generation Firewall Enterprise. Do not proceed to deleting the endpoint until the association deletion is complete. Attempting to delete an endpoint with active associations will fail. Deleting firewall endpoint. With the association removed, we can now delete the firewall endpoint itself. This is an organization-level resource, so ensure you have the appropriate permissions. First, list existing endpoints to confirm the target. The G-Cloud Network Security Firewall Endpoints List command with zone and organization flags shows endpoints in your specified zone owned by your organization. You should see your Cloud NGFW zone endpoint listed. The delete command uses G-Cloud with the quiet flag to skip confirmation prompts. The Network Security Firewall Endpoints delete sub-command takes the endpoint name composed of org prefix and zone. The zone flag specifies the endpoint location, and the organization flag indicates the owning organization. Endpoint deletion takes approximately 20 minutes because Google Cloud must decommission the underlying inspection infrastructure. This is the reverse of the creation process that also took 20 minutes. You can run other cleanup commands while waiting, but do not attempt to delete the security profiles until the endpoint deletion completes. To verify deletion progress, run the list command periodically. Initially, the endpoint may show a deleting state. Once the list returns empty or no longer shows your endpoint, deletion is complete. If the endpoint deletion fails or hangs, check that all associations were successfully removed. An endpoint with remaining associations cannot be deleted. Also verify your IAM permissions include the ability to delete organization-level firewall resources. Deleting security profile group and profile. After the firewall endpoint is deleted, we remove the security profile group and the underlying security profile. These must be deleted in order. The group first, then the profile. The first command deletes the security profile group using G-Cloud with the quiet flag to skip confirmation. The network security profile group's delete sub-command takes the group name composed of org prefix and SPG. The organization flag specifies which organization owns the resource, and the location is global since these are global resources. Security profile group deletion is typically fast, completing in seconds. Once complete, any firewall rules referencing this group would become invalid, though we will clean those up separately. The second command deletes the security profile itself. The G-Cloud Network Security Profiles Threat Prevention Delete command removes a threat prevention profile. We pass the profile name composed of org_prefix and SP threat. Again, the organization and location flags identify the resource. Profile deletion is also quick. After both commands complete, all Cloud Next Generation Firewall enterprise-specific resources are removed from your organization. The only remaining resources are the standard networking and compute components we created for the LAN environment. If either deletion fails with a reference error, it means something still depends on the resource. For the security profile group, check that no firewall roles still use it. For the security profile, ensure the group was deleted first. Deleting load balancer components. Now we clean up the base infrastructure, starting with the network load balancer components. These must be deleted in reverse order of creation. Forwarding role first, then backend service, then health check, and finally the instance group. The first command deletes the forwarding role using G-Cloud Compute forwarding roles delete with the quiet flag. We pass the role name composed of prefix and NLB-IPv4. The region flag specifies where the forwarding role exists. This removes the public entry point for the load balancer. The second command deletes the backend service using G-Cloud Compute Backend Services Delete. The service name is composed of prefix and NLBs. The region flag indicates its location. With the forwarding route already gone, the backend service has no dependencies. The third command deletes the health check using G-Cloud Compute Health Checks Delete. The health check name includes prefix, region, and HC-HTTP80. The region flag specifies where the health check was created. Once deleted, no health probes will be sent to your instances. The fourth command deletes the unmanaged instance group using G-Cloud Compute Instance Groups Unmanaged Delete. The group name is prefix followed by IG. The zone flag indicates where the group exists. Note that deleting the instance group does not delete the instances themselves. They are read in the next step. Each deletion typically completes in seconds. After all four commands finish, the load balancer infrastructure is completely removed, and the external IP is no longer forwarding traffic. Deleting compute instances. With the load balancer removed, we now delete the compute instances. We remove both the web server and the client instance we created for testing. The first command deletes the web server instance using G-Cloud Compute Instances Delete with the quiet flag. The instance name is composed of prefix, zone, and www. The zone flag specifies where the instance runs. When this command executes, Google Cloud terminates the virtual machine, releases its resources, and removes the associated disks. The second command deletes the client instance using the same syntax. The instance name is prefix, zone, and client. The zone flag matches where we deployed it. Instance deletion typically takes 30 seconds to a minute per instance. Google Cloud must gracefully shut down the operating system, detach network interfaces, and release the IP addresses back to the subnet pool. If you have any secure shell sessions open to these instances, they will be disconnected when the instances are deleted. Make sure to exit any secure shell sessions before running the delete commands to avoid confusion. After both instances are deleted, the subnet will have no running workloads. The VPC still exists with its firewall policies, but no compute resources remain to generate or read or receive traffic. Note that if you created any additional instances during your testing, you should delete those as well before proceeding to network cleanup. Removing IAM bindings and tags. Before deleting the tags themselves, we optionally remove the IAM role bindings we added for tag administration. Then we delete the tag values and the tag key. The first optional command removes the tag admin role binding. We export user ID by querying G-Cloud auth list for the current account. Then G-Cloud projects remove IAM policy binding removes the role from your project. The member flag specifies your user account, and the role flag indicates roles/resource-manager.tag-admin. If you did not add this role during setup, you can skip this command. The second optional command removes the tag user role binding using the same pattern with roles/resource-manager.tag-user. Next, we delete the tag values. Each G-Cloud Resource Manager tags values delete command removes one tag value. We delete the client tag value first, passing the full path composed of project ID, the tag key name, and the tag value name. We repeat this for the server tag value and the quarantine tag value. Tag value deletion automatically removes any bindings to instances. Since we already deleted the instances, the bindings are already orphaned, but the deletion command handles cleanup regardless. Finally, we delete the tag key using G-Cloud Resource Manager tags keys delete. The key path is project ID followed by the tag key name. Once the key is deleted, all associated tag values and their bindings are permanently removed. With tags cleaned up, no IAM-governed tag resources remain in your project. Deleting firewall policy and association. Now we remove the Network Firewall Policy and its VPC association. The association must be deleted before the policy itself. The first command deletes the policy association using G-Cloud Compute Network Firewall Policies associations delete with the quiet flag. The firewall policy flag specifies which policies association to remove. The name flag identifies the specific association using prefix and FW policy association. The global firewall policy flag indicates this is a global policy. Association deletion is quick, typically completing in seconds. Once removed, the firewall policy rules no longer apply to your VPC. Traffic would fall back to implied rules and any remaining VPC firewall rules. The second command deletes the firewall policy itself using G-Cloud Compute Network Firewall Policies delete. We pass the policy name composed of prefix and FW policy. The global flag indicates this is a global policy. When executed, this removes the policy container and all rules defined within it. Policy deletion also completes quickly. After both commands finish, no custom firewall policies remain associated with your VPC. The VPC now only has the implied allow egress and deny ingress rules that every VPC has by default. If the policy deletion fails, ensure the association was successfully removed first. A policy with active associations cannot be deleted. Also verify you have the compute.network admin or equivalent role to delete firewall policies. Deleting Cloud NAT and router. With the firewall policy removed, we clean up the Cloud NAT gateway and Cloud router. The NAT gateway must be deleted before the router because NAT depends on the router for its BGP functionality. The first command deletes the Cloud NAT gateway using G-Cloud Compute Routers NATs delete with the quiet flag. The NAT name is composed of prefix, CloudNAT, and region. The router flag specifies which cloud router this NAT gateway belongs to. The router region flag indicates the router's region. NAT deletion stops outbound internet connectivity for private instances in the VPC. Since we already deleted the instances, this has no practical impact, but it is important to understand the dependency. The second command deletes the cloud router using G-Cloud Compute Routers delete. The router name is prefix followed by CR. The region flag specifies where the router was deployed. Router deletion removes all BGP sessions and routing configuration associated with the router, deleting subnet and VPC. The final cleanup step removes the subnet and VPC network. The subnet must be deleted before the VPC because VPCs cannot be deleted while they contain subnets. The first command deletes the subnet using G-Cloud Compute Network's subnets delete with the quiet flag. The subnet name is composed of prefix, region, and subnet. The region flag specifies where the subnet exists. Subnet deletion releases the IP address range back to the VPC. Since all instances and other resources using this subnet are already deleted, the deletion should succeed without dependencies. The second command deletes the VPC network using G-Cloud Compute Networks delete with the quiet flag. The network name is prefix followed by VPC. VPC deletion removes the network and all its configuration, including any remaining firewall rules and routes. This is the final step in completely removing the LAN environment. After both commands complete, verify the cleanup by listing networks in your project. Run G-Cloud Compute Networks list and confirm that Cloud NGFW VPC no longer appears. You can also check the Cloud Console's VPC Networks page to visually confirm the network is gone. Congratulations! You have successfully completed the Cloud Next Generation Firewall Enterprise Lab, including the full cleanup. Your project is now restored to its pre-lab state with no residual resources. Thank you for your attendance. Please consider subscribing to the channel and liking this video.